The rapid evolution of defensive fortifications in the interwar period, culminating in the deep, multi-layered concrete networks of the French Maginot Line, presented military planners with a terrifying tactical dilemma. To breach these heavily fortified sectors, assault pioneer units were traditionally tasked with hand-carrying heavy satchel charges, flamethrowers, and Bangalore torpedoes directly to the firing slits of concrete pillboxes. This manual approach to demolition was inherently suicidal, resulting in catastrophic casualties among highly trained engineering specialists even before the main infantry assault could be initiated. In search of a mechanical solution to bypass this slaughter, the German High Command's Ordnance Office, the Heereswaffenamt, initiated a secret program in 1940 to develop a specialized, unmanned demolition vehicle. Designers envisioned a small, tracked machine that could be steered remotely from the relative safety of a friendly trench line, transporting a massive high-explosive charge directly to the base of an enemy bunker, bridge, or tank track before detonating. This search for an unmanned breaching asset led to the acquisition and rapid adaptation of a design prototype originally conceived by the French engineer Adolphe Kegresse. Following the fall of France in 1940, German forces recovered Kegresse's experimental prototype near Paris and tasked the Bremen-based automotive manufacturer Borgward with refining and mass-producing a combat-viable derivative. Borgward's engineers scaled down the design, creating the Sd.Kfz 302, officially designated as the Leichter Ladungsträger, but soon widely nicknamed the Goliath by the soldiers who deployed it. The Sd.Kfz 302 was an incredibly compact, low-profile tracked vehicle, measuring just 150 centimeters in length, 85 centimeters in width, and 56 centimeters in height. Its miniature chassis was divided into three primary compartments. The central compartment housed a massive 50 to 60 kilogram main demolition charge of high-density explosive, while the flanking compartments contained the complex electrical drive systems, battery banks, and track steering mechanisms. The initial propulsion system of the Sd.Kfz 302 was a high-tech marvel of modern electric engineering, relying on two silent, 2.5 kilowatt electric motors manufactured by Robert Bosch. These motors were powered by a massive array of lead-acid batteries, providing the vehicle with an exceptionally quiet acoustic signature that allowed it to creep across no man's land under the cover of smoke or darkness with almost zero warning. The tracks were driven by a complex, dual-clutch transmission that allowed the remote operator to steer the vehicle by varying the current and rotation speed sent to each motor independently. The Heereswaffenamt believed that this silent, low-profile mechanical demolitionist would revolutionize the mechanics of siege warfare, providing infantry divisions with an unstoppable, disposable battering ram that would render traditional concrete fortifications obsolete without sacrificing a single German life. The structural engineering and battery technology of the early electric Sd.Kfz 302 represented a pinnacle of German precision manufacturing, but this sophistication introduced a crippling economic reality that doomed the program from its inception. To maintain complete silent running and precise remote control, the Robert Bosch electric motors and their associated heavy lead-acid battery banks were built to the highest civilian, marine, and electrical tolerances. The complex electrical relays, gold-plated wire contactors, and high-purity copper windings required to sustain the massive power draw over a 60-minute operating range made the production of each individual Sd.Kfz 302 incredibly expensive. The Heereswaffenamt was horrified to discover that each electric Goliath cost approximately 3,000 Reichsmarks to manufacture. This astronomical price tag was particularly hard to swallow given the weapon's fundamental design philosophy, which dictated that the entire 3,000 Reichsmark vehicle, including its expensive electric motors, battery banks, and precision transmission, was entirely disposable and would be completely vaporized upon reaching its target. To put this economic absurdity into perspective, the cost of a single disposable electric Goliath was almost equal to the manufacturing cost of a fully reusable military motorcycle, a Kettenkrad track tractor, or multiple standard infantry anti-tank guns. Recognizing that the cash-strapped German war economy could not sustain the mass production of a 3,000 Reichsmark disposable toy, Albert Speer's Armaments Ministry demanded a radical redesign to slash production costs and simplify the manufacturing chain. This led to the introduction of the Sd.Kfz 303 in late 1942, which abandoned the expensive, high-purity copper and heavy battery packs of the electric version in favor of a conventional, two-cylinder, two-stroke Zundap petrol engine. The Zundap engine, originally designed for lightweight civilian utility vehicles and small agricultural pumps, was cheap to mass-produce, instantly slashing the unit cost of the Goliath from 3,000 Reichsmarks down to approximately 1,000 Reichsmarks. While the petrol-powered Sd.Kfz 303 succeeded in reducing the immediate economic drain on the Reich's treasury, the change introduced a host of severe mechanical and tactical compromises. The quiet, stealthy whisper of the electric Bosch motors was replaced by the loud, high-pitched, agricultural buzz of the two-stroke Zundap engine, which could easily be heard across hundreds of yards in a quiet combat zone, immediately alerting enemy sentries to the Goliath's approach. Furthermore, the Zundap petrol engine was notoriously temperamental and fragile, requiring constant mechanical maintenance to prevent the delicate carburetors from clogging with dirt, mud, and dust on the battlefield. The transition from the high-tech electric toy to the cheap, petrol-powered drone demonstrated how the economic realities of a disintegrating industrial base forced the German military to trade technical sophistication for crude, unreliable alternatives. The defining operational vulnerability of the entire Goliath series lay in its primitive, highly vulnerable guidance mechanism, which stood in stark contrast to the modern wireless remote control technology of the post-war era. Radio frequency remote control was considered by German designers, but it was quickly rejected due to the severe threat of Allied electronic jamming, which could easily hijack or neutralize the explosive-laden vehicles, turning them back onto friendly trenches. Instead, designers opted for a physical, wire-guided tether system that connected the vehicle directly to the operator's control box via a 3-strand telephone-style cable. This control cable, measuring 650 meters in length, was wound around a heavy, spring-loaded steel spool mounted in the rear compartment of the Goliath, spooling out behind the vehicle as it crawled forward across no man's land. The physical tether functioned as the vehicle's single point of failure, representing a literal and figurative umbilical cord that was constantly exposed to the violent, chaotic environment of the front lines. The 3-strand copper wire had to be thin and flexible to fit on the rear spool, meaning it possessed almost zero tensile strength and was completely unarmored. On an active battlefield, this delicate copper thread was subjected to a relentless barrage of environmental hazards. The heavy, grinding tracks of advancing German tanks, the sharp fragments of exploding mortar shells, and the flying shrapnel of artillery blasts would frequently sever the wire, instantly isolating the Goliath from its operator. The moment the cable was cut, the current ceased, and the vehicle's internal safety relays engaged, instantly locking the brakes and leaving 100 kilograms of live, unstable high explosives sitting helplessly in the open. The vulnerability of the control wire was so pronounced that Allied soldiers quickly developed simple, low-tech countermeasures to neutralize the feared Beetle tanks. During the Allied landings at Anzio and the Normandy invasion, British and American infantrymen quickly realized that they did not need to waste valuable anti-tank ammunition to destroy a Goliath. Instead, standard infantrymen would wait for the vehicle to crawl past their positions and then simply run out with wire cutters, shears, or even bayonets to cut the trailing cable, immediately rendering the high-tech German drone useless. The snapped copper nerve proved that no matter how advanced the internal mechanics of a weapon might be, a primitive and exposed control system will always reduce the entire system to a useless pile of scrap metal under the stress of real combat. Beyond its economic and guidance vulnerabilities, the Goliath was severely crippled by its physical dimensional limits, which made it highly unsuited for the shattered, cratered terrain of World War II battlefields. Although the vehicle was equipped with steel tracks and an independent suspension system on paper, its diminutive size meant its actual ground clearance was a microscopic 11 to 16 centimeters. In the mudlogged trenches of the Eastern Front, the rocky hills of Italy, or the debris-littered ruins of Normandy, A ground clearance of barely 6 inches was a recipe for structural paralysis. The flat, steel belly plate of the Goliath acted like a sled, constantly high-centering the vehicle on minor rocks, tree roots, discarded gear, and frozen clods of earth. When the Goliath encountered a shell crater or a steep-sided trench, its short length of only 150 centimeters prevented it from bridging the gap. The vehicle would frequently nosedive directly into standard infantry trenches, getting stuck vertically with its tracks spinning uselessly in the air, or flip over completely onto its back like an armored turtle. The low-profile suspension lacked the travel and dampening required to absorb impacts at its top speed of barely 6 miles per hour, frequently causing the tracks to jump off their drive sprockets when traveling over rough ground. The throwing of a track was an irreparable failure on the battlefield, as the remote operator had no way to realign the steel track from a distance, leaving the vehicle stranded and vulnerable to capture. The structural helplessness of the Goliath was a source of constant frustration for the combat engineers of the Panzerpionier battalions. Units charged with deploying the Goliaths frequently reported that they spent more time trying to steer the heavy, clumsy vehicles around minor obstacles than they did actually moving towards the target. In many cases, engineers were forced to leave the safety of their trenches under heavy enemy fire to physically lift, push, or drag a stuck Goliath out of a shell crater or mud hole, completely defeating the purpose of an unmanned vehicle designed to protect them from danger. The structural reality of the Goliath proved that miniature tracks are no substitute for true ground clearance, as the vehicle remained a terrestrial prisoner of the very terrain it was built to conquer. The defensive protection of the Goliath was another critical engineering failure, as designers had severely compromised the thickness and quality of the armor plating to keep the overall weight of the vehicle manageable for transport. The electric Sd.Kfz 302 was clad in a mere 5 millimeters of mild structural steel, which was insufficient to stop anything larger than standard pistol ammunition or distant rifle fire. While the petrol-powered Sd.Kfz 303 upgraded this shielding to 10 millimeters of hardened steel on the front plate, the sides and rear remained extremely thin and highly vulnerable. This lack of robust armor meant that the Goliath was not an armored wedge that could shrug off infantry resistance, but rather a fragile, slow-moving glass cannon that carried its own death sentence. The extreme vulnerability of the Goliath was magnified by the massive, highly concentrated nature of its cargo. Unlike a traditional tank, which uses its armor to protect a crew and complex internal machinery, the Goliath's primary purpose was to transport up to 100 kilograms of highly explosive TNT or hexogen directly to the target. This meant that 80% of the vehicle's interior volume was filled with volatile explosives. A single well-placed shot from a standard Allied M1 Garand rifle, a British Lee Enfield, or a Soviet Mosin Nagant could easily pierce the thin side armor and detonate the main charge. The moment a rifle bullet or a piece of shrapnel penetrated the casing, the Goliath would explode in a spectacular, catastrophic fireball long before it reached the enemy lines. This vulnerability created a terrifying hazard for the German pioneer crews who were tasked with operating and deploying the vehicles. Goliaths had to be prepared, fueled, and armed directly inside the German frontline trenches, often just yards away from friendly infantry assemblies. If an Allied sniper or machine gunner spotted the Goliath being prepared and managed to score a lucky hit on the vehicle while it was still inside the German lines, the resulting explosion of 100 kilograms of high explosives would completely obliterate the friendly trench section. Entire squads of German combat engineers and infantrymen were killed by their own Goliaths detonating prematurely in their assembly areas. The premature trap of the Goliath turned what was supposed to be a revolutionary weapon into a highly feared liability, as German soldiers realized that the tiny tracked mines were far more dangerous to their own side than to the enemy they were meant to destroy. The final historical evaluation of the Sd.Kfz 302 and 303 Goliath program reveals a stark and sobering contrast between the futuristic promises of Nazi propaganda and the grinding economic reality of a nation facing total collapse. Between 1942 and 1945, The German armaments industry produced an astonishing 7,564 Goliaths across all variants. On paper, this massive production run suggested a highly successful and widely adopted weapon system. But the actual operational impact of these thousands of vehicles on the course of the war was practically non-existent. The vast majority of the Goliaths produced never saw active combat, instead sitting idle in supply depots due to a lack of fuel, battery replacements, or specialized training teams, or being captured intact by advancing Allied forces who viewed them as technological curiosities. The true cost of the Goliath program must be measured in the immense macroeconomic opportunity costs that it imposed on the collapsing German war machine. The production of over 7,000 remote-controlled vehicles consumed thousands of tons of high-grade structural steel, immense quantities of copper for electric motor windings, and miles of precision-manufactured insulated copper wire for the control cables. This massive diversion of vital raw materials directly starved the production of practical, highly effective defensive weapons that Germany desperately needed. The copper and precision electric motors wasted on the disposable Goliaths could have been used to manufacture thousands of additional high-frequency radio sets, electrical components for fighter aircraft, or wiring arrays for U-boats. The high-grade steel could have been easily redirected to produce hundreds of additional anti-tank guns or thousands of anti-tank mines, weapons that would have extracted a far higher toll on Allied armored divisions. Ultimately, the Goliath was a high-tech gimmick, an expensive, over-engineered mechanical toy that was completely unsuited for the harsh, unforgiving realities of total war. While it represented an interesting conceptual precursor to the modern military unmanned ground vehicles of the 21st century, it was a tactical and economic failure for the nation that built it. The attempt to bypass the human cost of combat through complex, disposable robotics only served to accelerate the industrial exhaustion of the Third Reich, proving that in the crucible of real combat, an expensive and fragile gimmick will always succumb to the simple, robust, and economically sustainable weapons of the enemy.